So we're still continuing our exploration of molecular orbital diagrams, and today we're going to see a few more examples of them to see how they work and how we can use them to better understand some things that valence bond theory just does not allow us to do. So it's just a reminder, in the last video, we made a molecular orbital diagram for H2. We said, hey, let's start with our atomic orbitals, make our molecular orbitals here in the center. Hydrogen here has a 1s, hydrogen here has a 1s. They both have one electron. We form our two molecular orbitals. One goes high, one goes low. That's our linear combination of those two spherical orbitals. So here is, for example, the plus combination. Here's the negative combination. We see one has a node in between. Therefore, it's something that we look at as an anti-bonding orbital. It's saying that, hey, we can't have electron density between the two atoms. Whereas down here, we saw that we do get buildup of electrons between the nuclei, so we do form a bond. We worked out an electron configuration, we worked out the bond order, and said that, hey, a single bond was formed in this case. So that's what we did in that last video, just in the quick nutshell. So now we're going to do some molecular orbital diagrams for some molecules we couldn't do with valence bond theory, specifically H2 plus and H2 minus, and see what we learn about these cases. So again, they're based on the same thing. So we, again, have our 1s orbital for each of my hydrogens. We're going to make our molecular orbitals here in the center. One goes high, one goes low. In this case, we're not really going to worry about anything because it's still the same orbitals. Everything looks the same here. What is going to change now is how many electrons we have. So let's think about this for a second. When we are dealing with H2 plus, it just has one electron. We started with 2 electrons to make the positive ion there. We have to lose an electron, so that means we only have 1 electron. Let's go ahead and put it in here. So now we can use this and say, okay, it looks like there's 1 electron in this molecular orbital. We can do our bond order calculation to find out that we have a half order bond here, which is something we couldn't do with valence bond theory. Half order, what does that even mean? The important things to realize here is that H2 plus is a stable molecule. We can find that out in the environment. It exists in interstellar space. It's there. It exists as a molecule. Using valence bond theory, we had to share electrons, so it didn't make sense why a 1 electron molecule was held together. But now we can see with molecular orbital theory, there is an explanation for why this molecule exists in the first place, which is pretty good. Yeah, let's look now over here at the case of H2 minus. So again, it's the same diagram. We're still using our same orbitals, our 1s's on either side. We're going to form our same molecular orbitals. Nothing has changed here. Again, what has changed is how many electrons. Now we have a total of 3 electrons, because now we have our 2 from our starting case. We're making an anion, so we're adding 1 to it. So now I've got to occupy 3 electrons. So let's put them in. 1, 2, that molecular orbital is full. 3. That's how we fill a molecular orbital diagram, just like we did with atomic orbitals. All right, let's take a second here. Let's calculate the bond order. How did we do that? Give you a second here to think. Yeah, we did the same equation, 1/2, our number of bonding electrons, which in this case is 2, minus the anti-bonding, which is 1. So we have 1/2 of the quantity 2 minus 1. This is, again, 1/2. This is also an important result because H2 minus is also a stable molecule. We find this in a lot of unique places, and it does exist stably. Again, something that we could not predict with valence bond theory. It didn't make sense there. Whereas here now, nice and easy explanations. It all fits together here. So that's the case for just using something simple here to describe some anions, specifically of H2. We could go a little bit further here for a second to say, well, what does this actually mean here? Well, we found out that both of these ions here have a bond order of half, which does tell us something that now we can quantify. We say, well, half of a bond, well, that's definitely weaker than a single bond. So we would say it has a weaker bond in each of these cases than it does in H2. Also, this will correspond to these having a longer bond than H2. So, for example, in H2, the average bond length is about something like 0.7 angstroms. We would expect H2 plus, H2 minus to be larger than that, maybe 0.8 angstroms, 0.9 angstroms, somewhere in those range. Hopefully that makes sense, because when we have a weaker bond, it doesn't hold the atoms together quite as well, so therefore they can drift farther apart. So this is the real great thing, is now we can even make some structural arguments on what these molecules start to look like. And that's really powerful for us. And we can go even beyond simple hydrogen. We can do other diatomics. So let's do the molecular orbital diagram for helium dimer. Ooh, there's a weird one. Let's see what it tells us. Well, if we look at each of our atomic orbitals for helium, they're still the same 1s orbital. So this diagram looks basically identical, again, to hydrogen. So this is where we can use what we know about other systems to learn about something new. We're still using those same orbitals. We still form a sigma G1s, a sigma star U 1s. So we have the bonding down here. We have the antibonding here. There's our node that we have. All this is the same here. So the only thing different, again, is how many electrons we have. And if we look at helium dimer, each one of them has 2 electrons. So that's a total of 4 we have to put in. We'll put in 2 here. We'll put in 2 here. So if we actually work this out now, look at our bond order calculation. 1/2 of 2 minus 2, that's equal to 0. There we go. A result that actually does make some sense to us again. When we say, oh yeah, helium, we say doesn't make any type of molecules, so we shouldn't expect a bond forming between them. So He2 plus, or He2 plus, He2 rather, is not a stable molecule. We will never find it out in the universe. And just because I know you love how much we lie to you in chemistry, I just told you that you will never find He2 out in the universe. Let me know if you actually think that's true. And we can apply these now to do ions of He2. So we can look at He2 plus, He2 minus. So let's see what we've got here. If we're dealing with helium dimer as a cation, this is a 3-electron system. If we are going to look at it as an anion, this would be a 5-electron system. So we'll have to think about that here in a second. But let's fill these in. So when we're dealing with He2 plus, we've got 3 electrons, 1, 2, and 3. So could we predict if He2 plus is going to be a stable ion, or will it stay apart? What do you think? Hint. I'm going to do it slow. And we get a half-order bond here. So just like we saw with some other cases, here is a case where we have a real molecule that can form a molecular ion. He2 was not stable, but He2 plus is stable, which is pretty cool. And yeah, we've actually seen this experimentally. So there's a lot of experimental work that's been done on this. It's a pretty cool molecule. Let's look at now the anion. So we've got 5 electrons. So I've got 1, 2, 3, and 4. What do we do now? Uh-oh, what happens? Well, the thing that we have to remember is here we showed the 1s orbitals of helium, but don't forget, it can have 2s orbitals. They're up here. They're just not occupied in helium. So we could make a molecular orbital segment for this diagram out of the 2s orbitals. So in other words, we would have one level that went down, one that went up. So there's my connections I'm making. It's a little bit overlapped here, but I think you get the point that I'm making here. So now I could put one more electron in here. There's my 5. And now we could ask the same question. Is He2 minus going to be stable or not? And again, when we're doing this, you just have to calculate the bond order. I'll leave that up to you. I'll probably ask you what is the bond order of He2 minus in class, so make sure you work that one out. So that takes care of how to deal with s orbitals, but p orbitals start to make things a little bit more complicated. So let's look at molecular orbitals now for things that are in the columns for boron, carbon, and nitrogen. So we're over in the p block on the periodic table on the left-hand side here. So just like we did with the helium example, hey, we said we could have our 2s, so we're going to make a bonding and an anti-bonding, just like we did with the 1s, so nothing new here. But with the p, there's a lot more going on here. Why? Well, I have a total of 1, 2, 3, 4, 5, 6 p orbitals in my example here. So maybe we're thinking about boron dimer. We want to know, what is this an actual stable molecule that we could look at? So, all right, now we're looking at those p orbitals. And this is where some of the nomenclature is going to get a little bit more confusing here, but we'll get to understanding this more when we deal with symmetry, because now we're going to see that we have some new labeling here where I have these pi u orbitals, I have pi star g orbitals that are showing up here. We'll talk about what those mean later when we talk about symmetry. So for right now, it's more about memorizing, the pattern that we have here. We're going to do 2 degenerate orbitals, a single orbital, 2 degenerate, 1 single orbital in my pattern. That is what builds off of having these 6 p orbitals interact. Because remember, when we're making a molecular orbital diagram, we start with a total of 6 p orbitals here. I need to have a total of 6 molecular orbitals. Well, 2 plus 1 plus 2 plus 1, that's 6 molecular orbitals again. So we're staying consistent here. We are generating orbitals that are both bonding, which are now kind of below this line here, whereas the anti-bonding are above that line. They have the stars on them. All right. So this is what these would look like. Let's do this for actually boron. So we know that boron would have 2s electrons, and then it has 1 p electron. Doesn't really matter where I put it, so I'll just put it there. So now we can start putting these into our molecular orbitals. I would have 2 electrons here, 2 electrons in this orbital, and now we get up to a decision point, because remember, we've got 2 more electrons that we have to deal with. Which orbitals are we going to put them into? This is the same thing as Hund's rule. We're going to keep them split until we have to pair them. So 1 and 2. That fills all of our electrons, and now we have our complete molecular orbital diagram. Question: is this paramagnetic or diamagnetic? I'll ask you that in class 2. Now, unfortunately, because of effective nuclear charge, we see as we move across the periodic table, there is a switch in these orderings. So when we're looking at the groups that contain oxygen, fluorine, and neon, we see a different pattern here. So now with our p orbitals, we have 1, 2, 2, 1. But again, we have them split. We have the lower set, which is our bonding. The upper set is our anti-bonding orbitals. But so again, why this happens here, this is just a consequence of the effective nuclear charge, and it happens to swap the ordering of the states here. So a little bit of a pain in our butt here that we have to remember 2 sets here, but that's all we've got to worry about here. Now we can use this for any of these types of groups. So in this example, I said, hey, let's look at fluorine. So let's make molecular fluorine F2 here. Let's look at how many electrons we have. We'd have 2s, and we'd have 2p5. So I've got 5 there, 5 there. Let's start putting them into our molecular orbitals. 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. That should be all my electrons now. All right. This is another case where I'll say, hey, we should actually look at this one and figure out what we've got here. So make sure you calculate the bond order of this system here and let us know, does it actually make sense? What do we expect for F2 as a species? You can use your valence bond picture. It should get you the same answer here. So make sure you do that. Make sure you know what that actually is. Now, the previous examples, we've only been dealing with homonuclear diatomics. We can do heteronuclear diatomics. So instead of thinking of things that are the same, we could be thinking about a diatomic that is different across here. And this is where things will get a little bit fun because now we're looking at two different atoms. The sides of our molecular orbital diagram will move around because they're different energetics, because they're different atoms. This is going to be something that's not really that we can predict qualitatively. We'd have to do some severe PChem calculations. We're not going to worry about that. So what we need to know at this level is that our orbitals will still interact and form these molecular orbitals if they are of similar energy and they are of appropriate symmetry. Same thing we said for in all cases. So those are the two that we'll have to keep in mind for when we're doing heteronuclear diatomics. Probably the easiest example we can do here is that when we combine the atomic orbitals of H and F so that we can form the HF molecule here. And so we see a lot of things happening here. So for example, if we were to actually find out what the energetics look like, we'd see that the 1s of hydrogen is similar in energy to the 2p. The 2s, though, is far below, and there's no other orbitals here. So the 2s electrons, they actually don't have anything that they can do. I mean, there is a now what we would call a non-bonding orbital because we see no connection back to the other side here. It only is coming from the fluorine. So we'd say that we have two non-bonding electrons on that fluorine. Okay, let's think a little bit more. Up here, we're now trying to mix an s and a p orbital. Well, remember, we have to have the same number of orbitals that we started with at the end of the day. So I have 1s, 3p, so I should have 4 molecular orbitals. So I have 1, 2, 3, and 4 here. This was where things get a lot more complicated because, hey, we've only got the 1s orbital here. It can only make 2 orbitals here. That means 2 of these p orbitals are just kind of left over here doing nothing. Again, they act as non-bonding electrons here. So again, these get a little bit more complicated when we have to deal with this. We're not going to be drawing these. I'll have to give you information to be able to do that. But basically, we're saying, yeah, we can still do it. It just gets more complicated. We can still use it in the same way, but we just have to recognize non-bonding orbitals do not affect the bond orbital. They're not bonding, they're not anti-bonding, they're just non-bonding. So on fluorine in HF, if we drew our Lewis diagram, we would have these 6 electrons over here that are non-bonding. Well, looky here, I've got 2, 4, 6 electrons that are non-bonding. Ta-da! So we see similarities across the board here. So a lot in here, a lot of examples. It's complicated, I know, and I gave you some things to work through. So as always, let's talk about this more in class. Make sure we've got this under our control here and we understand what's happening. And if not, we can ask questions. All right. So until I see you next time, be excellent to each other.